Hi. So I wanted to make a video about Runge-Kutta, what it is conceptually, and how we use it. So the general idea behind, first off, any sort of differential equation computational method is that our goal is to find the analytical solution to some differential equation. So maybe I give you a differential equation that's something like 3 dy dt or dy dx plus 2y is equal to, I don't know, e to the minus x or something random like that. And if you were to go through your typical differential equation techniques, you want to find what y is. What is, and I'll put it in blue, y of x. And the reason I'm putting it in blue is because it might be graphed. This might be the answer to that differential equation. It's not. This is arbitrarily drawn. But what this is saying is that if I pick some random point, xy, if I look at the value of y and the value of x, and also the derivative at that point, which is the same as the slope, do that in a different color, whatever that might be, that'd be this guy, that equation would be true for that specific point. And it would be true for any point on the curve. That's the goal. We're trying to find the y that satisfies that equation, which says that if I multiply the value of y at a given x by 2, we take that given x and exponentiate it here, and then also find what the slope is or the derivative is at that same point, that equation would be true. So this is the thing that we always look for, is this blue curve, the answer. I'm going to write this. I'm going to erase this. I don't need that. Okay, let's go ahead and say that this is our solution to our differential equation. Now, sometimes the equation is very complicated and we are unable to solve them using simple techniques. So that's when you use different types of numerical methods to find them. And what we ultimately find is that instead of finding this continuous curve that's a complete function, we find discrete data points that ideally fall on the curve. So I'll just kind of erase this for a second. I'll bring it back. But we're trying to find the data points that go on the curve. And every iteration of some sort of differential equation numerical method will give us the next point. And then we'll use this point to find the next point. We'll use this point to find the next point, and so on. That's kind of the idea behind this. Let me go back a bit. Okay. And one of those techniques that we use to find those points is Runge-Kutta. So I'm going to erase this again. This is kind of the exact way we would do it. We'd solve the differential equation. But if we're using some sort of computational way, we would use Runge-Kutta, which says that y, it's typically written as I plus 1. But I'm just going to focus on trying to find the x value or the y value at some point x1. So this would be y1 is y0 plus a1 k1 plus a2 k2 times h, where h is the distance between the 2 points. And we specify that. That's our step size. This is our step size. That's what we specify. In this example, we see that this, based on the way that I drew it, is h. Now, if what's interesting is that if you were to solve for this thing, this weird thing, you would get that this weird thing, put as a question mark, literally, why not? This is y1 minus y naught over h, which is x1 minus x naught, which is y1 minus y naught over x1 minus x naught. So this thing is kind of like a slope. This is like a slope. That's the general idea about it, is that we are trying to find some representation of a slope. I hope we see that. All I did was just subtract this over to the other side, and then I divided by this h, and we see that this term, they just label it as a question mark, is equal to rise over run. It's like a slope. Let me erase that. So what are these values? So K1 is the slope at our current data point. I call it F, which is how they call it. Say this is dy dx at our current data point, which a lot of times is given the variable f, where f is the slope. So like for this picture, at x naught, y naught, we have a slope here that's tangent to this point. The slope of this line is K1. K2 is the slope at some nearby point. That's not necessarily at x1. It might be some other point. This would be x naught plus p1 times h. We'll discuss what these p's and a's are in a second. Y naught plus q plus k1 q11 times h. So again, if we write this in terms of f, this would be f of x naught plus p1 times h, y naught plus k1 q11 times h. So let's discuss what these are. If you think about x naught, that is our starting point on our graph. Let me zoom out a bit so we can see. This is our starting point on our graph in the x-axis. And now I'm going to add some multiple of h, where p1 is the multiple. So if p1 is 1, that means that I will be looking at the slope at x1, or using that as my x value of the point I want to evaluate a slope at. If p1 was, let's say, a half, what that would mean is that my x that I'm computing for this K2 is actually right in the middle, half of h. If that's what P1 was, I would end up using that as my x coordinate for the point I'm going to evaluate the slope. So basically, at least in terms of x, this is going to be a nearby point. Nearby in regards to x naught, our current point, or our initial condition in the way that I'm doing this problem at the moment. Similarly, y naught will also be a nearby point, but we see that we have this k in here. We have some k times h. And if you think about what I said before, how K1, just look at this point for a second, y naught plus K1 Q11 times h. This K1 is the slope at the current point. This is f of x naught, y naught. That's what we would compute beforehand. If you multiply a slope by h, you're basically looking for a delta y. So f of x naught, y naught times h is like some delta y. Just like how P1H is some delta X, we'll see that K1 times H is some delta Y, where this Q1, again, is just some multiple of this delta Y. So similarly, what we would do, we see that this equation is y naught plus this. So here's our y naught. This point here is our y naught point. Perhaps when we do this type of math, we end up getting a y value that is, let's say this is where our x1 is. This is our x0 plus 1/2 h, let's say, for our x relative to x naught. Maybe we end up getting a y value that's like here. So this is going to be, I'll do it in red maybe. This is going to be our y naught plus some q11 k1 times h. Essentially what we're doing is, based on the slope of the tangent line, we're going to use that to help us determine our next y value. So basically, we'll end up with k2, which will be the slope of the differential equation at that point. Again, we don't know this blue thing, but if you were to go ahead, we'll change the green again. We're going to change different colors. Sorry. If you were to go ahead at this point, which we're trying to line up with that, this is the point x naught plus half h, y naught plus q11 k1 times h. This is the point on our differential equation that we don't know, but we do know what dy dx is from the differential equation itself. This will be the slope at that location. So that is k2. So this is k2, whatever it may end up being. This red guy was k1. So I have two slopes. So these two things, these are two slopes. One at our initial point, or our known point, and one at a neighboring point. So we have these two slope values. What do we do with them? Well, if we come back up to here, we see that this term, which is like a slope, knowing that a1 and a2 are constants, that expression, a1 k1 plus a2 k2, is like a weighted average of slopes. So essentially what we're doing is we're looking at the average of these two slopes to try to figure out a better idea of what the trajectory of our curve is. Basically, we're using what we currently know and what's ahead of us to try to actually get an estimate of what the next point is. That's our objective. Because really what we're trying to estimate is this point x1. So if I were to take the average of those two slopes, maybe it gives me a slope that looks like this. And that might give me my next point. That's the conceptual idea behind it. So let's just go ahead and kind of write down, or maybe do an example of what this would be. But I guess before we do that, what Runge and Kutta did was determine the four equations that we would need to determine what type of weights we use for our A1 and our A2, and what kind of multiples we use to evaluate our points. That's P1 and Q1. And what they learned or derived is that these weights have to add the 1, which kind of makes sense if you think about it like a percentage. We'll give 60% to K2, 40% to K1. So those values, the decimals, have to add the 1. They learned that A2P1 was a half. And they learned that A2Q11 is also a half. And again, note, this is for the second order Runge-Kutta method. We're not talking about fourth order. So these equations would be different for a higher order Runge-Kutta, but for our purposes, this is good enough. So the issue is we have 4 unknowns, but only 3 equations. That's a problem because we can't solve it. So what we end up seeing is what they do is they assume some value of A2. Not Runge-Kutta, other people assume some value of A2. And then we can find out what the other variables are. So an A2 value is assumed. So the people that assume things, one person was Heun. That's a very common method you'll see with Runge-Kutta. Heun's method. Heun says, okay, we're going to assume that A2 is equal to a half. That's what Heun decided to assume. So this is assumed. Then we need to figure out what the other coefficients are now that we've eliminated one of our unknowns. Now we have 3 unknowns and 3 equations instead of 4 unknowns because we've assumed that one of the values is a half. So if we look at our first equation, we have A1 plus A2 is equal to 1. This will mean that A1 is also equal to a half. We have A2 P1 is equal to a half. If A2 is a half, that will mean that P1 is equal to 1. And similarly, A2 Q11, that would mean that Q11 is also equal to 1. So we have our solutions. And if you think about the A2 and the A1, they're both a half. If we come up to original equation, what that implies is that we were giving equal weighting to the slope at our current point and the slope that's ahead of us, because these both are 0.5. They're each 50%. So we were equally weighing them. We're basically taking the average of those values, the slope where we currently are and the slope ahead, to get an estimate for what our next y value is. So with that in mind, let's try to do an example. And the example that I did in class was that I gave you the differential equation, and maybe I'll write it differently just for the sake of how we would do this. Let's say I have x plus y minus dy dx is equal to 1, and we know that the initial condition y of 0 is equal to 2. So in order to do this, or any type of first order ODE method, we want to solve for dy dx. So solve for dy dx. So that'll give us that dy dx, if we move some things around the equal sign, that ends up being x plus y minus 1. So this is the actual slope of the exact solution. We don't know what the solution is, but we know its slope. It's based on the x and y coordinates of the point. So what we want to do is try to estimate, the question is estimate y at 0.5 using a step size of 0.5. So let's go ahead and write out, or first conceptually see what we're doing. So if I were to draw a graph, we see that our first point is y of 0 is 2. So this is our first point. I'm not loving the grid lines here. It's okay. Let's say I say that 1, 2, 3, 4, 5. Let's say that this point is 1. Therefore, this point would be a half. Our goal is to figure out what our y value is in this location. We don't know what it is. So what we're going to do is determine what our current slope is and what our slope at a nearby point is to estimate what that is. So we'll come back to this picture. Our equation is y1 is y naught plus a1 k1 plus a2 k2 times h. Where we found the a1 and the a2, those were both a half. This ends up being y naught plus, I can factor that out if I want. Now I'll leave it in. Half a k1 plus half a k2 times h. And they gave us h. H is 0.5 in the problem, because that's what we're trying to find. They gave us a step size that ends up being equal to the point of interest. So k1 is the slope at our current point, which for our problem would be the slope at 0, 2. Remember that f is the slope. So if we come up to our equation, we see that this is an expression for the slope. dy dx is x plus 1 minus y. dy dx is x, or x plus y minus 1, apologies, x plus y minus 1. This is the same thing of f of x, y. This is equivalent. So we'll plug in 0 for x and 2 for y, and we will find out that f of 0, 2 is 0 plus 2 minus 1 is 1. This is equal to k1. Basically, everything we're doing now is equal to k1. Well, not that. This would be k1. That's the slope at our current point. So if I were to draw a tangent line, maybe with some slope of 1, that is what the slope is at the current point. Again, we don't know what the actual differential equation is, but at that point, we know that the slope happens to be 1. I'll draw a little bit smaller. That's our slope. Let's pretend that that's a slope of 1, because nothing's to scale in this drawing. Now, k2 is the function, the derivative of x naught plus the multiple of h. So in this problem, we ended up getting that P1 and Q11 were both 1. That's what ends up happening with Heun. This would be 1 times H, because again, this is P1. This would be Y naught plus K11 times Q11, which is also 1. Specifically for Heun's method. Remember, that changes depending on which method you're using, but for Heun's, that's what we end up getting. So if we were to plug in things, this would be the function at x naught, which is 0 plus h times 1, which is a half. Our initial condition for y was 2 plus k1, which we just found up here. That was 1 times a half for h. So k2 will be the slope of the function at 0.5, 2.5. So that's the slope we want to find. So knowing that our slope, f of x, y, is x plus y minus 1, we can plug in our x value, our y value, and subtract 1. We get that k2 is equal to 2. So what that means is if I draw a point, 0.5 and 2.5, which would be here, based on the axes that I drew, this will have a bigger slope at that point compared to the first point. And this just so happened to be at 0.5 for Heun's method. It's not always at 0.5 or always at the y. It's not always at the x value we're trying to evaluate at. Like in this problem, we said y of 0.5. This second point could be something else depending on what P1 and Q11 are. But in this specific example, because they end up being 1, we end up evaluating the slope at this point 0.5. So now that we've done that, we know that y1 is y naught plus a1 k1 plus a2 k2 times h. We can plug in our stuff now. It's going to be 2 plus a1 was a half times k1 is 1 plus a2 was a half times k2 is 2 times 0.5. This would be 2 plus 1.5 in those parentheses. That's a half plus 1 multiplied by the h. That whole thing is 0.75, which means that our y1 value will be 2.75. That's what we end up getting for this problem. So what that means is our first point is at 0,2. Our second point will be something like at 0.5, it'll be 2.75 on the y-axis. So that is our estimate of what's happening at 0.5. We don't know what's happening in between, but our estimate for our differential equation solution, if you come back up to this original graph, the original solution was in blue. Again, not the same solution as this problem. This was just an example. What we end up seeing is that our estimate from Runge-Kutta and Heun's method is that this point ends up being 0.5, 2.75. And that's our answer. So from a conceptual perspective, what we're doing is looking at a weighted averages of the slopes, one at our current point and one at a nearby point. If we're doing this specifically for Heun's method, we are finding the average between the slope at our current point and the slope at x is equal to 0.5. Now the y value in this case ends up being 2.5. That's just what it ends up being for Heun's. Again, that's not necessarily on the curve, but what we are doing is trying to evaluate what the slope is based on those x and y values, and then using that to actually get a good estimate for what our next point is in the solution. Okay, if you have any questions, please let me know. I hope this makes sense. Okay.